Hello everyone. The title of this video is Defining Exponential Growth and Decay. So in this video I'm going to be doing examples taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.1, called Exponential Functions. And I'm under the heading Defining Exponential Growth, right, and Decay I added onto the title. Now each example I do will be either one of the examples from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Okay, so we have seen earlier in this section and in an earlier video the definition of an exponential function. Right, that was any function that could take on this form, f of x equals a times b to the x, where a was non-zero, and that was called the initial value, and b, the base, was a positive number that's not 1. Now, an exponential growth model, I'll add a little more to this, is when the base is bigger than 1. We're going to consider when a is positive for each of these cases. And when b is bigger than 1, you're going to have an exponential growth model. And when b is less than 1, but still positive, you're going to have what's called exponential decay. Right? And this value of b is called, the growth factor, or growth multiplier, or decay factor, decay multiplier per unit x. So I'll write that out here. Now, my first examples, and all the examples really in this video, are just simply going to be asked to determine whether the equation represents exponential growth, decay, or neither. So again, we're looking for functions that look like this. F of x equals a times b to the x power, just a simple old x power. We're going to have a be positive, right? I know before a could be negative, but here when we're just talking about exponential growth and decay, we're going to stick to a being a positive number and see what happens. And b is not 1, but also positive, right? B is positive as well. So as I was saying, if that base is bigger than 1, you have exponential growth. All right, the exponential function, and we've seen several exponential functions by this point. The function will look like this. Be increasing as you go from left to right. The domain's all real numbers, the range is all positive numbers. Horizontal asymptote of the x-axis, like all the usual, exponential function properties, but it's an increasing function. As x increases, the output increases as well. The other case is if b is less than 1, but still positive, so between 0 and 1, like a half or a third or whatever. Then you have exponential decay, right? Meaning that you'll have a decreasing function. So something like this. So it still has all the same properties of an exponential function. Domain is all real numbers, the range is all positive numbers. Horizontal asymptote is the x-axis, so the graph will be approaching that to the right end this time though instead of the left end. And it's a decreasing function in this case. As x increases, the value of the output decreases. Right. So that's what we're looking at. So my first function, now it's not a function of x, it's a function of t, but it's still the same setup. we have p of t equals 1.25. That would be the value of a, this initial value, positive number, great. Times, and then b is 1.012 to the t power, right? Just plain old t. So it's very much the same form, but instead of x you have t. So the value of the base here is 1.012, and that's greater than 1. And the function is in this form, so we do have an exponential growth model here. Alright, and I'll show you what the function looks like. It should look something like this that I drew out here for the growth model when the base is bigger than 1. Let me go to that Desmos website, desmos.com, a free online graphing calculator. And I'm just going to enter the function the way we were given it. P of t equals 1.25 times, and then 1.012 raised to the t power. And I know it doesn't look like much here, but if you zoom out, eventually you'll see the exponential growth. Alright. And then again, it's got all those same properties. Domain's all real numbers, the range is all positive numbers. I know it looks like it hits the x-axis, but it doesn't, right? Or the t-axis in this case. If you zoom in close enough, you'll see the graph is not actually on the t-axis, right? It's above it, even just a little bit. Alright, but the graph is going up as you go to the right. Right, like I was saying here, it's an increasing function as you go from left to right. Alright, so exponential growth there. And then this growth factor of 1.012. This tells me also that when I increase t by 1, the output gets increased by 1.2%, right? This is 0.012 greater than 1, more than 1, and 0.012 is 1.2%. So you could say that the value of p increases by 1.2% each year, or something like that, if t was time in years, but I'm not going to get into all that right now. Okay. Next example. It's got pretty much the same look. P of t equals, some initial, this is the value of a, 1.39, it's a positive number, great. And then times, b to the t instead of b to the x, but no big deal, just change x into t. 1.006 to the t power. So the value, this does have that form, it is an exponential function. So now we just have to decide, is it an exponential growth function or an exponential decay function? Is it increasing as you go from left to right or decreasing? And again, that all depends on the value of b here, which is again greater than 1. So once again we have an exponential growth model. Alright, and if you'd like, just go back to that graphing calculator, go back to Desmos, and I'll just enter this p of t equals 1.39 times 1.006 to the t, and again you will see, if you zoom out far enough, you'll see that it is indeed an exponential growth function, an increasing function as you go from left to right. As t increases, p increases. Okay. So far we've seen a couple growth models. Let's see what the next one looks like. Alright, now the next one, y equals 300 times 1 minus t to the 5th this isn't even an exponential function. This is a polynomial function. Right? And again, you should be familiar with polynomials from Chapter 5 of this text, this OpenStax algebra and trigonometry text. So since this isn't even an exponential function, this has neither exponential growth nor decay. Neither growth nor decay, or neither exponential growth nor decay. Right, since it's not even an exponential function, I hope that makes sense, right? Right, it's not an exponential function because your base has a variable and the exponent is a number. Right, in exponential functions, the base is a number and the exponent has a variable. It's the other way around. And again, you can look at the graph of this, and you'll see that it doesn't have the properties of an exponential function graph. It doesn't have a horizontal asymptote. All right. In fact, here the domain would be all real numbers, and the range would be all real numbers as well if you were to take a look at a graph of this, but I'm not going to do that. But that doesn't happen in exponential functions. For an exponential function, the range won't be all real numbers. Right. Okay, so this time, for example 4, we have the y equals a times b to the x, or b to the t again. We do have that form. A is 11,701, a positive number, great. The value of b this time, the base, is less than 1, right? 0.97 to the t or to the x. But the value of b this time, the base, is 0.97, which is less than 1, meaning we have an exponential decay model on our hands here. And again, I'll show you. Go to the Desmos site. I'll just get rid of all that. Y equals 11,701 times 0.97 to the t. Right. And you can definitely see the decay, the decrease as you go to the right. Domains all real numbers, range is all positive numbers, horizontal asymptotes the x-axis. Again, the graph looks like it's touching the x-axis, but as I've shown you before, you zoom in close enough, it's not touching the x-axis. Right. Yeah, and again, base is less than 1, so you're going to get this decay. Now, if you want to say, 90.97, this is 1 minus 0.03, right? So you'd say that every time I increase t by 1, the output decreases by 3%. Right? 0.03 is 3%. So every time the input increases by 1, the output is decreased by a factor of 3%, 0.97, which is 3% less than the previous amount. If you want to say it that way, but you don't need to. I'm not going to. All right, so we've seen a couple of growth. We've seen a decay. We've seen an example that's not an exponential function at all. And that's going to be the case for this last example as well. Now, I know it looks like an exponential function. Right? Y equals 16.5 times, and then you have 1.025 raised to the 1 over x power. This is not an exponential function, though, by our definition. I know that the base has a number, positive number, that's not 1. And the exponent does have a variable, but you see that variable's in a denominator. That's not just the x power, x to the first power there. this does not satisfy our definition of an exponential function, right? That was y equals a times b to the x, where again b is positive, a is not 0, and it's just to the x power here, not 1 over x. Remember, for our exponential functions, the domain was all real numbers. Over here, the domain is not all real numbers. The domain is all values of x that aren't 0. Because if you plug in 0 for x, you're going to get 1 divided by 0 in this power. And you can't have zeros in denominators, right? That's undefined. So this is not exponential, right? This function here does not satisfy our definition of an exponential function. So if it's not even an exponential function, then it has neither exponential growth nor decay, kind of like example 3 with that polynomial function. And I'll show you this one. So I have neither exponential growth nor decay, just like example 3. And I'll punch this one in, and we'll see that there aren't even going to be points on the y-axis where x equals 0. There aren't even going to be points on the graph touching the y-axis. No y-intercepts. So y equals 16.5 times 1.025 raised to the 1 over x power. And yeah, see how this is kind of crazy. I mean, it looks like the y-axis is there, but like if I go back here, it's actually not being touched. You see the y-axis there? There are actually no points on the y-axis for this graph, even though it looks like there are. But if you zoom in close enough, you'll see that there are no points where x is 0. And this is clearly, I mean, you saw, this is not looking like any exponential function. Right? It actually looks more like a rational function in some way. Just very odd, this one. So it's not even exponential. It's definitely not, it decreases here, but you wouldn't say it's a decaying function because it's not decreasing from one value down to some horizontal asymptote the whole time. Right? So it doesn't take on exponential function properties. Right? Doesn't have satisfy the definition we have of an exponential function that I have in this little box over here. Okay, so I hope that's clear. And that's all I got for you. A couple of growth, 1 decay, a couple not exponential functions at all. And you should be able to identify whether a function is exponential or not based on our definition. And I had a video out earlier about identifying exponential functions. You should have seen that earlier in the section. And I'm hoping that watching me go through these 5 examples here help you out in some way. When you're asked to identify, whether or not a function is exponential, and if it, is modeling exponential growth or decay on your own. And thank you very much for watching.